Welcome viewers. In this video we are going to look stage 2 out of 7 for design of substation gantry foundation in Eurocode. In this stage 2 we are going to look foundation and soil parameter loads and load combinations. So this is entire detail about the design stages which we are going to look in future also. So in the first stage we already seen the overview of calculation. The link for the video is given in the descriptions. Second stage, in this stage we are going to look foundation and soil parameters, loads and load combinations. In the third, the stability check. Fourth stage we are going to look anchor bolt design. In the fifth is a design of a bottom slab. Sixth is a punching and one-way shear. And finally we are going to look design of pedestal in seventh stage. Now let's look into that calculation part. So in the screen you can see an Excel sheet which is we are using for calculating this gantry foundation design. So here that x direction means it is a parallel to conductor span, and y direction of the foundation means it is a perpendicular to conductor span. It means if the tower is located here, one more tower should be located just below, which is to be connected with the girder as showing in the screen. And the conductor will run along this direction. So this conductor spanning direction is called x direction for foundation representation, and the perpendicular to conductor, if the span or width of the foundation in this direction, then it is a y direction. So this is what the representation of the coordination in x and y for the foundation. So in x coordinates, that is x direction, we are having the length of the foundation as 4000 mm, 4 meter. Center to center distance of the pedestal, we are considering the 4 number of pedestal here for this tower, which is spaced as 2 meter in x direction. When looking into that y direction, the width we are considering as 3 meter, and center to center distance of the pedestal we are considering as 1.5 meter. And coming to the section of the foundation, z direction we can consider as vertical, and x is a width length direction which is parallel to the conductor span. So here that 4 meter length and 2 meter center to center distance of pedestal we already seen in the plan view. And here the above ground level the pedestal should extend to 300 mm, and the thickness of the raft we can consider as 400 mm. The depth of foundation below ground level we can consider as 2.5 meter. So this is the sketch of the foundation which we are going to do design in this stage 2 and followed by other stages. So these are the input foundation size in words. So the pedestal numbers is 4 and the sizes are 600 mm which we had seen in the plan view. Bottom pad size is 4 meter by 3 meter. Distance between pedestal in x direction is 1.5 meter. So it should be y and x. And the depth of foundation we had seen here 2.5 meter. Bottom pad thickness is 400 mm plinth level is 300 mm. Next one is a water table level from finished ground level. So this is as per the soil report we need to consider. If it is 0 means then the water level is in the ground level, so that we need to consider the submerged condition for entire foundation. So suppose this water table level as per the soil report shows it is 0 meter. It means the water level is at here, exactly in the ground level. So then the entire concrete and the overburden soil will subject to submerged condition, that is water filled weight we need to consider. So for that the reduction will be there in the density of the soil and the concrete. We need to consider that also, because that there will be a chance of flotation if the foundation is having the less weight compared to the actual load which is carrying using the tension due to the wind or other horizontal forces. So this is what we need to consider. So here the 0 means we are going to calculate the submerged condition for the entire foundation, and the density of subsurface water is 9.81, that is 1000 kg per meter cube. So we are converting into a SI unit, so it is 9.81 kilonewton per meter cube. And the grade of concrete we are assuming as a C30 37. Here that C means it is a compressive strength of concrete as a C, and 30 means it is a compressive strength of concrete in a cylinder, and 37 is a compressive strength of concrete in cube. Grade of steel we can assume as B500B. There are other two types also, B500A and B500NC. Generally this NC is mainly applicable for the area where the seismic is applicable. So for the severe seismic location we need to consider this B500NC, and B500A is a ordinary or a normal construction we can consider, but for important type of construction we need to consider this B500B. Dry density of concrete we are considering 25 kilonewton per meter cube, and the submerged density of the concrete we need to detect this surface water density, so that it is 15.19 kilonewton per meter cube. Similar like for soil parameters, density of soil is 18 kilonewton per meter cube we are assuming, or as per soil report we need to consider, and submerged density is, in that we need to deduct this 9.81, that is density of subsurface water, and the depth we already consider as 2.5 meter, and submerged depth is D minus water table level. So water table level is 0, that is at finished ground level. So the full depth of foundation we need to consider here 2.5 meter, and bearing capacity we can assume as 300 kilonewton per meter square. In general, for good foundation, for good soil for this foundation, we need to have 150 kilonewton meter square above. We are assuming here 300, and coefficient of sliding and between soil and concrete we can assume as 0.26. Generally, this can be arrived from geotechnical report, or geotechnical report will give, instead of giving the direct value of coefficient of sliding between soil and concrete, there will be angle of internal friction is provided. So that angle of internal friction is nothing but this 22 as mentioned here. Generally it will vary from 18 or 15 to 30 degree. So that we need to take from the soil report. So if it is 30, then tan 30 into 2/3 we need to consider as a coefficient of sliding between soil and concrete. So finally the gross SPC we need to consider at the depth of foundation. So because this you need to consider along with the overburden soil also. So this how we are calculating is 300 kilonewton per meter square is a net SPC at foundation depth. Then the overburden soil density is 18 kilonewton per meter cube multiplied by the 2.5 meter. Adding this to the net bearing capacity, we are getting the gross bearing capacity. So this is all about soil parameters. Then we need to calculate the weight of the foundation along with the soil which is below the ground level. So weight of the overburden soil is density into the depth of the foundation into the sizes of the foundation, and deducting this pedestal and the raft. So we are getting the weight of overburden soil and weight of concrete is nothing but multiplying the dry density with the concrete volume 4 into 3 into 0.4 plus 4 into 0.6 into 0.6 into 2.1 is the height of the pedestal. 2.1 we can arrive from 2.5, that is depth of foundation minus raft 0.4. So that volume multiplied by 25 kilonewton per meter cube, we are getting 206.4 kilonewton. So similar like total weight, we are adding these to soil and concrete weight. So these are for the dry density, and the distance between foundation base and the pedestal top. This is to calculate the moment. This is to calculate the moment which is transferred to the depth of the foundation from the top of the pedestal. So adding the depth of the foundation and the pedestal, that is plinth level, pedestal above ground. So 300 plus 2500 is 2.8 meter. So maximum eccentricity and minimum eccentricity we need to calculate based upon the foundation sizes. So for the maximum eccentricity it is L by 3. So the length we are considering 4 meter, 4 by 3 is this value, and 1 3 by 3 is a width direction, and the limiting eccentricity is nothing but L by 6 or B by 6. So L by 6 means it is a 4 by 6. The length we are having a 4 meter divided by 6, and width is a 3 meter. 3 by 6 is a 0.5 meter. So it means that in any case the moment, the bending moment divided by the vertical load is a actual uh, eccentricity that should not exceed this maximum eccentricity. But if it is exceeding this limiting eccentricity, then we need to consider some special designs, a special method of design for calculating the bearing pressure. So that we will look in the stability case, that is in the stage 3 of this series of video, and calculating the submerged condition weight. Weight of overburden soil is a wet condition is we are calculating this way. That is the density we are considering is a submerged density of the soil into the total size of the foundation is 4 by 3. In that we are going to deduct that raft thickness and the 4 number of pedestal, 4 into 0.6 into 0.6 into 2.1. So by this way the dry density is, sorry, the wet density of the concrete, wet density of the soil is calculated, and the dry density anyway here it is 0 because the soil is fully submerged because of the water table is at the ground level, and this is a summation of that. If it is a partially submerged, then this dry weight will come for certain height. Say suppose we are considering here 0. Instead of that, if your water table is at 1 meter from the ground level, then there will be some dry density weight also. So this according to calculation where whichever the projected above the soil which is above the 1 meter, we need to consider that. And the next one is we need to consider the concrete submerged weight. So weight of concrete here you can see that as it is fully submerged, the entire mass below the ground we need to consider as a submerged condition. So the mass of the concrete below submerged condition means up to that 2.5 meter we need to consider. So that is 4 into 3 into 0.4 plus 4 number of 0.6 into 0.6 into instead of whole height we need to consider 2.1 into the submerged density 15.19, so that we will be getting 118.85 kilonewton. And also the dry density of the concrete, which is the concrete weight which is above the ground, we need to consider this 4 number of pedestal 4 into 0.6 into 0.6 into 0.3 is a height above the ground into the density, dry density of the concrete we are considering here. So summation of this weight of concrete 129.65 kilonewton. So summation of the soil, overburden soil and the concrete weight, it is 311.27 kilonewton. So these are the foundation and soil parameter we need to calculate manually. Next we will look into that loads and load combinations. So in the screen you can see that a tabular form of primary loads, load combination of a serviceability limit states SLS, and the load combinations for ultimate limit states ULS. So let me look into that primary load cases. So as you know that these are the primary loads which is applicable for the gantry foundation design. So before that, let me look into that our previous load calculation for structure. So on the screen you can see that substation gantry structure loads which we had done previously for that gantry structure design. So the link for this video also given in the descriptions, you can look into that. So how to calculate these primary loads? So these are there are 20 number of loads we had calculated during the structure design. Now it is a foundation design and we need to list out the primary loads from this list out of the 20. What are the load cases are applicable? In European standard, the short circuit force we should not consider for foundation design because it is a short term load, very short term load, maybe 1 second or 3 seconds. So this 1 second or 3 second load will not transfer to the foundation. It is a research done by the European standard norms. So in that it is specified no need to consider the short circuit force, mainly for the gantry structure. If even for the equipment support structure, if you are not going to consider the short circuit force also, well and good, because as per the standard norms the short circuit force is a very short term, even the wind case also there are some hours of wind is applicable, but for this very short 1 to 3 second of short circuit will not cause any impact on the foundation. Even the transfer the foundation force from the structure within 1 or 3 seconds will not happen. Between this 1 or 3 seconds, the entire system is going to disconnected because of the short circuit forces. Then it means the force will not transfer to the foundation. So in that case, short circuit force is ignored for foundation design. And coming to the minimum temperature. So this minimum temperature also not applicable for foundation design, as the temperature variation will not affect the foundation as it is below the soil. So these three cases we can ignore. And in order to reduce the foundation calculation, we can also ignore this moderate wind load calculation, as the high wind and the extreme wind will give you the design data for both snow consideration and without snow or ice consideration. So from 15 to 20 we can ignore. So when coming to that wire tension there are 6 number of wire tension we had calculated during structure design, but in this case we are going to consider only wire tension 0 degree deviation with 0 degree Celsius of conductor temperature. So only these two we are going to consider, that is 3 and 6. Why it is? Because this minus 20 degree Celsius is applicable only for the construction and maintenance activities. So we are going to design our foundation for the entire lifespan. So this construction and maintenance activities will happen in a short period or once in a while, or the frequency of the construction and maintenance load is very nominal or very less, so we can ignore this minus 20 degrees Celsius also while doing design of a foundation. So in this case the 4 and 7 can be ignored, and wire tension for 40 degree Celsius for both deviation and without deviation cases of conductor. So for minus 40 we need to consider for minimum temperature case, as we are ignoring this 20 case number 20 minimum temperature T minimum. So we can also ignore this minus 40 degree also. So these are the red color with the strike through load cases are ignored now for the foundation design. So applicable foundations are only these 1, 2, 3 and 4, 5, 6, 7, 8, 9, 10. So only the 10 load cases we are going to consider for our foundation design. So here the 10 cases are done. Now we need to replace these values with the structural loads which we already calculated during our previous videos. On the screen you can see that robot structural analysis which we had calculated during the structure design. So from here we need to take the reactions. So as you see here that wire tensions which is parallel to y-axis. So as per our foundation calculation we had considered the x is the parallel to the conductor span. So that y force which we extracted from the reaction should be in x direction. So that we will see later. And here we need to click the results, click reactions, and here we need to select the simple cases. So in the simple cases we need to copy paste this table values until the node 8. So here there are 29 load cases. So this Excel already prepared to find the foundation reaction. So we are just pasting here. So here that load case 1 to 29 is available. But here look into that this calculation, this longitudinal force F of x for foundation reaction is considered as F of y. As you know that calculation is foundation calculation is different than the robot structural analysis in terms of axis, y-axis and x-axis. So here you can see that y is parallel to the conductor span, because this tension we always used to apply parallel to the conductor for a flexible conductor. So this is why the sign is changing here. For longitudinal force F of x, while considering the foundation design, we need to consider F of y of foundation reaction from the structure. So similar like for transverse force F of y, that is perpendicular to conductor, we need to consider F of x, because as you see in the robot structure, x axis means it is a perpendicular to conductor span. So it's, and here in the right hand side you can note that what are the load case which are applicable for the foundation reaction, like dead load without ice, dead load with ice, wire tension 0 deviation, with the 0 degree Celsius, wire tension 30 degree to 30 degree deviation, vertical and horizontal 30 degree deviation, with 0 degree Celsius temperature, extreme wind 0 45 90 and high wind 0 45 90. So these are the load cases which is applicable for the foundation design as we discussed just earlier. So now we will do calculate how to find these total forces and total moment for the foundation. You can see in the right hand side these pictures. So these 4 grid 1, 2, 3 and 4 are the pedestal or main leg. Again here 5, 6, 7, 8 are the structure main leg for 2 towers which we had already seen in the structure model. So these 3 line red, orange and blue are the conductor spanning direction. So it means the x direction is parallel to the conductor span and y direction is a perpendicular to conductor span as per our foundation picture. So you can see in this Excel sheet the picture of foundation sketch, which is showing x direction is parallel to conductor span and y direction is perpendicular to conductor span. So with the 4 pedestal, the similar dimension I had considered here, but one change we need to do as per this structure. So here you can see that the structural model which we had prepared in earlier stage is having the center to center distance as 3 meter by 2 meter, but our foundation parameter calculation we have considered 1.5 by 2. So this we need to change to 2 to 3. So here that Excel calculation is prepared like if the length is less than this inadequate to hold this center to center distance and plus the pedestal distance, then it will show in red color. So that's why it's showing. So we can consider 5 meter as a total width of the foundation. So now we are considering the actual dimensions of center to center distance which is considered for structure design. So 2 meter is a smaller width and 3 meter is the higher width. So this is a slight modification in foundation dimensions which we need to consider as per the structure. So now come to this load calculation reaction. Yes. So in this picture you can see that 3 meter is a x direction center to center distance as per this foundation sketch, and 2 meter is the parallel to y direction. So same dimension we are considering here, parallel to y direction. So these are the 2 tower which are connecting with the girder to hold the 3-phase conductor which is traveling in x direction. So now we need to calculate the total forces. So this x, as you see that the structural model is in the conductor span is in y direction, but in our foundation design we are considering the conductor span as x direction. So Fy equal to Fx, Fy of the structure result equal to Fx of the foundation. So that's why we are considering this Fy as a Fx, longitudinal force for the foundation design, and the transverse is Fx, and vertical we are considering directly as F of Z. So likewise we need to find out for, we need to select 2 and for 3 and for 4. So likewise for all the node we need to link this cell here. So then the total horizontal force X is this one, and the total horizontal Y is adding this all sum Similar like for vertical, we are adding the total sum, and calculating the moment we need to review this sketch. So here you can see that m of x means it is rotating in this direction. So the lever arm required is 2 meter. So we are considering here the 2 meter, that is a width parallel to y-axis we are considering here. So 2 divided by 2, half of the distance is the lever arm. Similar like in order to calculate the moment along y, we need to consider this distance as a lever arm, because the moment of my will cause with respect to this two pedestal in one side, other two pedestal in another side. These two pedestal 3 and 4 will cause a tension together, and this 2 will cause a compression, so that this movement will be effective. So this lever arm distance, which is parallel to the bending moment direction, we need to consider, so that 3 meter is considered here. So we need to add all the this 2, 1 and 2 we need to add first, and 3 and 4 we need to do subtraction, so that we will be getting the resultant force of tension and compression of this 4 pedestal, and that multiplied with the lever arm distance we will be getting the bending moment. So the similar same case we need to apply here also, my. So we are adding these two and subtracting with the other two opposite legs, and multiplied with the lever arm distance, we are getting the moment here. So likewise we need to do for all the cases, and maximum force we need to consider in hx, hy, and vz, mx and my for all the cases. The formula remains same for all the cases. So we are just extracting this structure force and converting those into the foundation forces, because the foundation seems to be a rigid one, but we as a structure we design all the 4 legs as a hinged type. So if all the 4 legs are connected as a hinged type to the foundation, then the entire whole main leg will act like a fixed base together, so that we need to find out the bending moment also on the center line of the foundation. So this is what we done here. Now the calculation is done for the foundation forces. You can see, you can check here also, so that wire tensions which is acting in x direction. So while it is acting only in the x direction, there won't be any forces in y direction. So you can see here the value here is 0, even though the legs are having some certain forces in transverse direction. So those are one leg is subjected to -7, another leg is subjected to +7, and here you can see that leg number 2 is subject to 1.09, and leg number 4 is subject to -1.09. So summation of all these forces will give you 0. So this is like a resultant force which is acting at the foundation. So that's why if the wire tension is acting parallel to x direction, then we will be getting only the parallel forces, that is hx. So that is what derived here. And similar like for bending moment, for moment here, so if the x force is acting towards this, then the y-axis will tends to be bend. So that's why we are getting m of y alone. So it means that our formula which we got applied for calculating the bending moment and the horizontal forces, that summation of the resultant forces is correct, we can say. So likewise we need to check, and in extreme wind case also you can see that wind acting direction is x in case of 0 degree. So it means we will be getting only the wind forces in x direction. Y direction is 0, you can see here, and similar like the bending moment in y direction we are getting here. And finally we are getting the summary of the loads. Here what we have linked is for dead load without ice cases we are selecting this maximum value rho. So similar like for all the cases, even for high wind 90-degree we need to select this case, this maximum value cells. So this is a main value we need for foundation design. So we need to just copy this and open the load cell, load tab in foundation design Excel and paste here. So now the primary load cases for the foundation is arrived. So coming to the load combinations. So these are the load combinations we are considered as a critical one. So high wind plus conductor tension and a dead load with ice. So these are the load cases we need to combine together. So again here without ice and with ice plus wire tension plus, but here we need to consider the conductor tension with the deviation, wire tension with the deviation. In this case also we need to consider this 90-degree. So now we can copy paste all this for Hx and Hy. So here you can consider as a dead load without ice. Similar like here, it should be wind acting 45-degree, extreme wind acting 45-degree, and here extreme wind acting 90-degree. So yes, now all the load cases for serviceability is okay. Okay, this should be here. So now we can copy paste this entire cell to here for with the deviation conductor, and only this we need to change, that is conductor with deviation 30-degree vertical and 30-degree horizontal. So all the 6 cases we need to do likewise. So we have completed for X, then we can copy paste for Y, V, Z and M of X, so that you can see that this case is dead load without ice plus wire tension with deviation plus extreme wind 0 direction. So this is like dead load without ice, wire tension, extreme wind 45-degree for moment M of X. So now this table is corrected, SLS load cases, and when come to that ULS ultimate load combinations, so these are the factors. 1.35 is a dead load we are considering, plus 1 as a variable loads for wire tension, and 1.5 is a leading variable for wind load cases. And similar like these cases, 1.35 is a dead load and 1.5 is a wire tension is a lead variable, and 0.9 as a wind load as a normal variable loads. So these are the combinations. Even there are also other critical combinations by reducing this 1.35 dead load to 0.9 dead load and having the variable as 1.5 and 0.9. And there are a lot of other load combinations also. So accordingly we need to provide the load combinations which is required for the design. So here we can see that 1.35 plus dead load, and here also the formula is having some error mistakes. Okay, now it is okay. 1.35 plus 1 plus 1 conductor wire tension with zero tension and wind, extreme wind for zero direction. So now this is corrected. So here again this to be 45 degree and the wind extreme to be 90 degree here, and we can copy paste all the other two HY, VZ and MX, MY. Now here also the formula is having mistakes. So here we can have it dead load, and here the dead load with ice we need to consider, and conductor with the deviation, extreme loads. So these are the three things we need to consider here. So here you can see that 1.35 of dead load plus 1.5 of conductor tension plus high wind we need to consider here, high wind in zero direction. So here the high wind in 45 degree deviation or 45 degree direction transverse. Here the transverse wind we need to consider, that is WH90. So now this also updated with all the three. Now these are the conductor deviation cases. Now we can copy paste this into here, and only change here is the conductor deviation 30 degree we need to consider. Similar like for this case also 30 degree. So now all the 6 cases we have corrected the formula, and HY, VZ, MX we can just copy paste the formula, because this will lead the same kind of formula which is moving to the next cell, which will pick the next cell. Likewise VZ, yes, like this. So now you can see that all the load combinations, all the values for primary loads, load combination in SLS and ULS cases are arrived. Now represent the compression, T represent the tension, and HR is a resultant horizontal forces, which we can arrive as a square root of HX squares plus HY squares. So this is applicable for all the cases. And why we are calculating this is in order to design the pedestal, these forces are required. Equation to calculate the compression is given here and the tension is given here. That is nothing but that moment x divided by Cx, that is the center to center distance, the lever arm distance, plus moment divided by lever arm distance in y direction, Cy divided by 2. So the total divided by 2 plus Vz divided by 4. V is a vertical force that we need to divide it, and we divided by 4 legs, and adding with the resultant forces arrived from the movement with the lever arm, then we will be getting the compression. By deducting or doing the minus of the vertical value divided by 4 to the moment divided by the lever arm distance, we will be getting the tension. So with this, the stage 2 we can end, and we will look next stage for stability.
Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.